So now we will study the normal or the Gaussian distribution. Now this distribution is considered to be one of the most important distributions in the area of probability and statistics. So let us see how what is the form of the normal distribution. So let us consider integral I, which is minus infinity to infinity e to the power minus t square by 2 dt. Now since this is a even function, this can be written as 2 times 0 to infinity e to the power minus t square by 2 dt. Now what I do is I put t square by 2 as z, then t dt becomes dz, it becomes e minus z, and then it turns out to be this. But this quantity is nothing but 0 to infinity e to the power minus z, z to the power half minus 1 dz, which is nothing but gamma half. So this turns out to be root 2 gamma half, which turns out to be root 2 pi. So what it suggests is 1 by root 2 pi minus infinity to infinity e to the power minus t square by 2 dt is 1. Now I can make the transformation t as x minus mu by sigma. So dt becomes dx by sigma, so 1 by sigma root 2 pi. When t is between minus infinity to infinity, x is also between minus infinity to infinity, then x minus mu whole square by 2 sigma square dx is 1. So that means this whole integral is 1. So that means, and this is also non-negative. So that means this can be taken as a PDF, and that is a PDF of normal distribution. So a random variable x is said to have the normal distribution with parameters mu and sigma greater than 0, which we write as x has normal mu sigma square, if its PDF is given by this quantity. Sorry, there is no 0 over here because it covers the whole real line. So its PDF is given by this. So because we have already seen that minus infinity to infinity e to the power minus x minus mu whole square by 2 sigma square dx is nothing but sigma root 2 pi. So that means total integral here will be nothing but 1. So if one tries to plot the PDF, one can see the mirror image. So the PDF is increases up to mu and then decreases, and the PDF on the right side of mu is a mirror image of what is happening on the left side of mu, because x minus mu whole square is same as mu minus x whole square. So clearly if x is normal mu sigma square, then fx mu minus x is same as fx mu plus x, which is 1 by sigma root 2 pi e to the power minus x square by 2 sigma square for every x between minus infinity to infinity. So this suggests that the distribution of x is symmetric about the point mu, or in other words, x minus mu has same distribution as mu minus x. So that means mu is the median, and if the mean exists, then the parameter mu is nothing but the mean of the distribution. Now the normal 0-1 distribution is called the standard normal distribution. So let us try to see how does a standard normal distribution, which is the normal distribution with mean mu and variance 1, looks like. So suppose that x is normal mu sigma square for some mu belonging to minus infinity to infinity and sigma greater than 0, then I know that x minus mu has the same distribution as mu minus x. So probability x minus mu less than or equal to x would be same as probability mu minus x less than or equal to x. So probability x less than or equal to mu plus x is same as this probability, which is same as probability x greater than or equal to mu minus x. This is nothing but a fx mu plus x. This is nothing but 1 minus probability x less than mu minus x. But probability x less than mu minus x is same as x less than or equal to mu minus x, because x is absolutely continuous. So which is nothing but fx mu minus x. So what you get is, if x is normal mu sigma square, then fx mu plus x plus fx mu minus x is always 1. In particular, if you have a normal 0-1 distribution whose distribution function suppose is phi x, then capital phi x plus capital phi minus x should be 1. So before this, let me just introduce the PDF and distribution function of normal 0-1. The PDF and distribution function of normal 0-1 distribution will be denoted by small phi and capital phi respectively. So PDF is phi z, 1 by sigma, sigma is 1, root 2 pi e to power minus z minus mu is z, so z square by 2 sigma square. So this is the PDF. And what would be the distribution function? Integrate the PDF from minus infinity to z phi x dx, which is 1 by root 2 pi minus infinity to z e to power minus x square by 2 dx. Clearly normal 0-1 distribution is symmetric about 0, because we have seen normal mu sigma square is symmetric about mu, and for normal, standard normal, mu is same as 0. Then this we have already seen. Fx mu plus x plus fx mu minus x would be 1. So for normal 0, 1, distribution function is phi. So phi of mu is 0, phi of x plus phi of mu 0 minus x would be same as. So phi of x plus phi of minus x should be same as 1. So in fact, interpretation of this is same as probability x less than or equal to x is same as 1 minus phi of minus x, which is 1 minus probability x less than or equal to minus x, which is same as probability x greater than minus x, or x greater than or equal to minus x. So if it is normal 0, 1, so suppose x was over here, a negative quantity, then probability x less than or equal to x would be over here, minus x would be over here. So these two probabilities are same. So in particular, this whole probability would be same as this whole probability, but total probability is 1. So I can say that phi of 0 is always half, which is fine, because for normal mu sigma square, since it is symmetric about mu, mu is the median. So that means phi mu is half. For standard normal, mu is 0, so phi 0 is half. Now let us do this result about normal distribution. So let x is normal mu sigma square for some mu belonging to minus infinity to infinity and sigma positive. Then z, which is x minus mu by sigma, always has normal 0, 1. So one can convert normal mu sigma square distribution into a normal 0, 1 distribution through this transformation. The next result is if z is normal 0, 1, then square of z is chi square on 1 degrees of freedom. So let's try to prove this. So what is the transformation which we are considering? H of x is nothing but x minus mu by sigma, x belonging to R. This is clearly 1, 1. What is our inverse transformation? X is nothing but H inverse y is mu plus sigma y. So that is why the PDF of z is equal to x minus mu by sigma is fx, H inverse y, which is mu plus sigma z. Jacobian is, because it is a linear transformation, so Jacobian is just sigma, so mod of sigma. Indicator, because indicator minus infinity to infinity z, because if x is between minus infinity to infinity, hx would also be between minus infinity to infinity. So this. And this, if you put over here, because fxx 1 by sigma root 2 pi e to the power minus x minus mu whole square by 2 sigma square. In place of x, put just mu plus sigma z, so it becomes sigma square z square, sigma square square gets cancelled, so e to the power minus z square by 2. This sigma gets cancelled with Jacobian term, so 1 by root 2 pi. So what it suggests is if you have a normal mu sigma square distribution, you can convert it into normal 0, 1 through this transformation, that is subtract mean and divide it by the variance. It's worth noting over here for normal distribution mu and sigma square, mu is nothing but the mean and sigma square is nothing but the variance. Let us do the second part. If z is normal 0, 1, then y is equal to z square has a chi square distribution. So let z is normal 0, 1 and y is z square. Then let us look at fyt, which is probability that z square is less than or equal to t. Note that if t is less than 0, z square less than some negative quantity would be 0. So for t less than 0, fyt is 0. For t greater than or equal to 0, fyt is same as probability z square is less than or equal to t, which is same as probability z lying between minus root t to plus root t, which is same as minus root t to root t 1 by root 2 pi e to the power minus z square by 2. So this is an even function, range is from minus root t to root t, so it becomes 2 upon root 2 pi 0 to root t e to the power minus z square by 2 dz. Now what I do is I put z is equal to let us say root x, z is equal to root z prime, let us say, right. Then dz becomes 1 by twice root z prime. What are the range? So it becomes 2 upon root 2 pi. When z is between 0 to infinity, z prime is z square, so it would be from 0. If it is 0 to root t, z is 0 to root t, z prime would be 0 to t, because z prime is z square. e to power minus z square, which is z prime by 2, then dz, which is 1 by 2 root z prime. So it would be e to power minus z by 2, then z to power half minus 1, 1 by root 2 gamma half. So this is how it turns out to be. So now I can write down these cases combined. So my phi t turns out to be e to power minus z by 2, z to power 2 by 2, root 2. So this is from 0 to t PDF. So that means this whole can be written as minus infinity to infinity fyz dz, where fyz is nothing but e to power minus z by 2, z to power half minus 1, root 2 gamma half dz if z is positive and 0 otherwise. So that means your distribution function can be written as minus infinity to t, a non-negative function fyz dz. But this is nothing but a PDF of chi-square 1 distribution. So this suggests that y has chi-square on 1 degrees of freedom. So if you have a normal 0, 1, if you square it, you get a chi-square on 1 degrees of freedom. Let us try to see the moment generating function and some other properties. So let x is normal mu sigma square for some mu belonging to minus infinity to infinity and sigma greater than 0. Then moment generating function of x is e to power mu t plus sigma square t square by 2 for any t belonging to R. Expected value of x, which is mu, which is same as median, and variance of x is same as sigma square. So as I was saying earlier, in the normal mu sigma square distribution, the parameter mu is nothing but the mean of the distribution, and sigma square is nothing but the variance of the distribution. Then if x is normal mu sigma square, I consider ax plus b, where a is not equal to 0 and b is real number. Then y again has normal. If it has a normal, then the parameters are mean and variance, and mean of ax plus b is nothing but a mu plus b. Variance of ax plus b is same as a square sigma square. Let z is same as x minus mu by sigma. Then we know that z clearly has normal 0, 1 by a result done before. Then expected value of z to power r is 0 if r is 135, and this is this quantity if r is 246. So all odd order movements of normal 0, 1 are 0, which makes sense because the distribution of z is symmetric about 0. So z has same distribution as minus z. So all odd order movements would be 0 provided they exist. So let us try to do these results. Before that, let me state another result. The coefficient of skewness in this case is 0 because normal distribution is symmetric about mu. So coefficient of skewness turns out to be 0, and its kurtosis turns out to be 3. So let us see for t belonging to R, mxt is expected value of e to power tx, which is e to power tx times density. Density is 1 upon sigma root 2 pi e to power minus x minus mu whole square by 2 sigma square. So this is 1 upon root 2 pi. Now I make the transformation x minus mu by sigma as z. So dx by sigma becomes dz. So 1 upon root 2 pi. E to power t, x becomes mu plus sigma z. And then here you get e to power minus z square by 2 dz. So I try to make this as a perfect square because this would be nothing but e to power minus 1 by 2 z square minus 2 sigma t z. That is what would come. And e to power mu t comes outside. So I have to make it perfect square, so I have to add and subtract sigma square t square. So when I subtract it, it becomes e to power sigma square t square by 2 over here, and then it becomes a perfect square. But I know that minus infinity to infinity e to power minus x minus mu whole square by 2 sigma square dx is always sigma root 2 pi. So that is why this integral, if one has to look at, in period of sigma this is 1, so this is same as root 2 pi. So root 2 pi get cancelled. So mxt turns out to be this, and this exists for any t belonging to R. So once I have a moment generating function, I can do many things with this moment generating function. So let us try to find out the moments. So psi xt, which is log of mxt, which is mu t plus sigma square t square by 2. So let's take the first derivative, psi x1t, which is mu plus t sigma square. Psi x2t is nothing but sigma square. So mean, which is nothing but psi x10, which is mu. Variance is psi x20 is sigma square. So as I said before, mu and sigma square are nothing but the mean and variance of the distribution. Also, x minus mu has the same distribution as mu minus x, implies that mu is also the median. So the parameter mu is the median as well as the mean of the distribution, and sigma square is the variance of the distribution. Now let's see what is the distribution of y is equal to ex plus p. To show that it has a normal distribution, I'll show that its moment generating function is that of a normal distribution. So let us see myt, which is expected value of e to power t ax plus b. So it is e to power tb, which is constant, comes outside, expected value of e to power atx, which is equal to e to power tb, then moment generating function of x at the point at, which is e to power tb. Moment generating function of x at the point at would be mu times the argument at plus sigma square, argument square, which is a square t square by 2. I combine the terms of t, so which is e to power a mu plus bt plus a square sigma square t square by 2. Now this is nothing but mgf of a mu plus b and a square sigma square distribution, normal a mu plus b and a square sigma square by distribution. So this proves that y has normal a mu plus b and a square sigma square as a variance. So any linear function of normal random variable is again normal. Now let's see what is the moment generating function of normal 0, 1. So mzt. Normal mu sigma square has e to power mu t plus sigma square t square by 2. Sigma is 1, mu is 0, so it becomes e to power t square by 2. I expand it. This becomes summation k is equal to 0 to infinity t to power 2k divided by 2 to the power k by factorial k for t belonging to r. Let us see for r belonging to 1 to so on, expected value of z to power r is nothing but coefficient of t to power r by factorial r in expansion of mzt. So note that all odd powers of t are not there. So that means their coefficient would be 0. So if r is 1, 3, 5, so on, expected z to power r is 0. If r is 2, 4, so 6, so on, so then coefficient of t to power r, so that means I put 2k as r, so k as r by 2. So I have to divide it by factorial 2k, then I have to multiply by factorial 2k, that is how factorial r comes. K is 2 to the power r by 2, factorial r by 2. So this is what expected z to power r turns out to be. So I also know that z is also same as x minus mu by sigma, has the same distribution as x minus mu by sigma if x is normal mu sigma square. So using this I can find the moments of normal mu sigma square distribution. So expected value of z cube is 0, which means expected value of x minus mu whole cube divided by sigma cube is 0, which is same as expected value of x minus mu whole cube is 0, which implies that coefficient of skewness beta 1 is 0. Expected value of z4 is factorial 4 divided by 4 into factorial 2. So this is the value which I put in the last expression, which turns out to be 3. So that means expected value of x minus mu by sigma whole 4 turns out to be 3, which is equivalent to saying that expected value of x minus mu whole 4 is nothing but 3 times sigma 4. So kurtosis, which is gamma 1, which is mu 4 upon mu 2 square, turns out to be 3. Let us see a few more observations. Suppose x is normal mu sigma square. Then for z is equal to x minus mu by sigma, so that z has normal 0, 1 distribution, fxx is nothing but probability x less than or equal to x, which is same as probability that x minus mu by sigma is less than or equal to x minus mu by sigma. But this is normal z, so this is same as probability that z is less than or equal to x minus mu by sigma, which is normal 0, 1. So this is same as distribution function of normal 0, 1 at the point x minus mu by sigma. So this is a very nice observation that if one has to get the probabilities about random variable x, which is normal mu sigma square, they can be obtained through probabilities for normal 0, 1, which are given by phi. So let tau alpha be the 1 minus alpha's quantile of normal 0, 1 distribution. That means this is a point such that on the left of it the area is 1 minus alpha, or on the right of it the area is alpha. So that is phi of tau alpha, which is same as 1 minus phi of minus tau alpha is 1 minus alpha. If x is normal mu sigma square, then I know that fx mu is half and phi 0 is half. The following table provides the quantiles of normal 0, 1 distribution for various values of alpha. So, if alpha is 0.001, so that means on the right of it, the area is 0.001. So, this is tau alpha. So, if the area on the, so this is the area. So that means if tau alpha is 3.092, then on the right of 3.092, there is only 0.001 area. And similarly, if one has to look at on the right of 0.25, there is a 0.615 area. So these tables for phi z for various values of z are available in various textbooks. So one can see those textbooks because this normal distribution turns out to be very useful in statistical inference problems. So that is why these tables also turn out to be very handy. So one can consider, for example, this example. So let x is normal 10, 4. Find probability x less than or equal to 6.08, probability x greater than 13.3, probability x greater than 7.44, and probability x less than or equal to 11.35. So let's first consider probability x less than or equal to 6.08. Convert it into standard normal 0, 1. So this is same as phi of 6.08 minus the mean, which is 10, divided by sigma, which is square root of 4, which is 2, which turns out to be phi of minus 1.96, which is 1 minus phi of 0.96. One can see from the tables which we listed in the last page, it turns out to be 1 minus 0.975. So it is 0.025. Similarly, probability x greater than 13.3 is same as 1 minus probability x less than or equal to 13.3. Now this one can convert into normal 0, 1. So 1 minus phi of 13.3 minus mean 10 divided by standard deviation 2. It turns out to be this. One can again see the tables in the last page. It turns out to be 0.05. Similarly, probability x greater than 7.44 is same as 1 minus probability x less than or equal to 7.44. So 1 minus phi of 7.44 minus mean 10 divided by sigma 2, which is 1 minus phi of minus 1.28, which is phi of 1.28. One can see again from the tables, this value turned out to be 0.9. Probability x less than or equal to 11.35 is same as phi of 11.35 minus the mean 10 divided by sigma 2, which is phi of 0.675. Again from the tables of last page, this turns out to be 0.75.